Hello my dear students in grade 10. This is my first video. I'm gonna talk to you today about the exponential function. This lesson in grade 10 in the Algebra 2 book, page 362, chapter 6, lesson 2. I have divided this lesson into 3 parts. This is the first part. It's talking about the graph of the exponential function and some examples. And the second part we'll talk about the transformations of the exponential function, and the third part will talk about the compound interest as an example of the exponential function. Let's get started. This is the first part. This carries the definition of the exponential function. It is a function from this type, fx equals b power x. This is the function notation, where b is the base and x is a variable. B is the base, means a fixed number, and x takes different values. B can be any real number. It could be 2 or 3 whole number, or a fraction between 0 and 1, like 1 over 3, 1 over 2, and so on. If B is a whole number, like 2, 3, it will be an exponential growth function, like this type. If the b is a fraction, like this one, it will be an exponential decay. Let's see how can we graph the first one. For example, if I have a function fx equal 2 power x, or 3 power x, or 5 power x, anything power x, how can we graph it? If you make a table of values like this, and give x some values like -1, -2, 0, 1, 2, and then try to get the corresponding values of y or the fx by substitution in this notation. For example, if you put x equals 0, it will be 2 power 0, which is 1. If you put x equals 1, it will be 2 power 2, which is 2 power 1, which is 2, and 2 power 2, which is 4. 2 power -1, which is half, and so on. And then trace the graph of the function. This is when x equals 0, the fx rises to the 1. When the x equals 1, the fx rises to 2. 2, it will be 4. And from the other side, -1x gives you a half, -2 gives you a quarter, and then trace it. You will find the function in this form, and it is an exponential growth because when x increases, the y increases. In example 2, this is an example for the exponential decay function. When the base is a fraction between 0 and 1, like half, 1/3, and so on. If we also make a table of values and give x some values and get the corresponding values of y, the difference is when x increases, the y decreases. So we call it an exponential decay function. So in the decay function, the b, which is the base, is between 0 and 1, or it can be like x equals negative, because, for example, you know that 3 power -1 equals 1 over 3, 2 power -1 equals 1 over 2, and so on. So the function can take the form 1 over 3x, or 1 over something x, or 3 power -x, because the negative changes the whole number into a fraction. This is the first part of the lesson, and there is an exercise in page 367 from 10 to 28. Let's take some examples from this exercise before going to part 2. Please follow me and go to this page. It's page 367. I'm gonna give you some examples, and you follow me from the book. The first part is from 10 to 15. Identify each function as linear function, or exponential function, or quadratic function. I think the first one, which is number 10, 10x plus 3. This is number 10. gx is equal to 10x plus 3. What kind of this function? Is it exponential? No, it is a linear function. Why? Because it's 10x. The exponential is something power x, like number 13. 13 kx is equal to 0.5 x minus 3.5. Yes, this is an exponential function. What type of this function? It's a decay. Why? Because 0.5 is half. We can say this is half power x minus 3.5. Since x is in the exponent and you have a base which is a fraction, so it's a decay function. Or you can say that it's exponential decay. Okay, this is two examples from the first group. The second group is from number 16 to 24. So the first group is from 10 to 15. This is page 367. The second group is from 16 to 24 in the same page 367. Tell whether each function representing exponential growth or decay. What's the difference between growth and decay? The base. If the base is a fraction, it's a decay. If the exponent, if the base is a whole number, like 2.5, so it's a growth. For example, number 16, y or fx equals 12 2.5x. Is this a growth or decay? It's a growth. Why? Because 2.5, which is the multiplier, is greater than 1. But in number 19, you have dx equals 0.125 half power x. It's a decay. Good. Also in number 23, you have fk equals 7 to 2 power negative k. Power negative k means 1 over 722. Yani I can say that this will be 1 over 722 all power k. So it's also a decay. This is the second group. The third group match each function with its graph. Let me take some examples from this part. This is from 25 to 28, same page. Match each function with its graph. For example, 25, y equals 2 power x. What graph of this? It will be number D. Why? Because it cuts the x-axis at the y-axis at 1. Because any number to the power 0 equals 1. So it will be number D. But 28, y equals half power x. So it's a decay. So it can be matched with number A, because also it cuts the y-axis at 1 and it goes down like this from both sides. But in number 26, this is critical, y equals 2 and 3 power x. First, this is growth because 3 power x. And what's the 2? The 2 will move the function up. So it will be like this. So it will not cut the y-axis at 1, it will rise up. Why? Because 3 power 0 equals 1. 1 times 2 equals 2. So it will intersect with the y-axis at 2. So this will be number C, and so on. Now I have finished the first part of this lesson. Let me move to the part 2. Part 2 is talking about transformation of the exponential function from its parent graph. The fx equal 2 power x is the parent graph, or any number power x. It is represented by a graph intersecting with the y-axis at 1. If it is 2 power x, it will be like this. 3 power x, it goes close to the y-axis when you increase the base. So this is the parent graph. What about having 3 multiplied by 2 power x? This 3 will stretch the function up. It will move it up like this. This is 3 times 2 power x, and this is 5 2 power x. So the 3 and 5 moves the function up. What about this? Fx equal half power x. This is the decay function, or 2 power negative x, because they are the same. Half power x equals 2 power negative x. It is a decay function. It's the parent graph of the decay, which intersects the y-axis at 1. What's if you have 2 power x plus 1? This 1 shifts the function up 1. So instead of intersecting at 1, it will intersect at 2 with the y-axis. And if you have 2 power x minus 1, it will shift the graph down. It will intersect at 0. And what about this 2 power x plus 1? If x changes to be x plus 1, so there will be a shift to the left, 1 unit. If this is 2, it will be 2 units to the left. It will look like this. 1 unit means you have to change or move the y-axis to the left. And this 2 power x minus 1, the minus 1 moves the graph to the right, and the positive 1 moves the graph to the left. And on this part we have an exercise, in the same exercise, in the same page, but numbers from 38 to 45. Let me give you some examples from this part of exercise. Also follow me from the book. I have from 38 to 45. From 38 to 45. The question is saying graph each pair of function and describe the transformations from f to g. 38, for example. You have fx equals half power x and gx is equal to 5 times half power x. How can I graph this and this in the same graph and see the difference and describe the difference? We know that this is a decay. Decay means intersecting the y-axis at 1 and goes in this way. What about this? This 5, we said that it will stretch the function vertically. It will be like this. And move it up. How come? If you put x equals 0, it will be 1 times 5, which is 5. So it will be like this. Means 5, and this is at 1. And goes very close to the y-axis. This is the difference. So what happened? How can I describe this transformation? I can say that gx is a vertical stretch of fx. That's all. Another one. Let me take 44. fx is equal to 3 half power x, and gx is equal to 3 times 2 power x. So this is growth and this is decay, and the 3 stretches the curve up. So in this one, the decay will be like this, but stretch it up, it will be at 3 instead of 1. And this is the same, but it's a growth. Okay, so this is this one and this is this one. So I can say that this is a reflection on the y-axis of this. Gx is a reflection on y-axis of fx. That's all. Right? Okay. And this part of exercise from 38 to 45. Let me move to the third part of the lesson. Part 3. It is talking about compound interest formula. The total amount of an investment A earning compound interest is this one, which is A equals B. You need to memorize this rule. P 1 plus R over N times T, where P is an initial amount, R is the rate, and T is the time, and N is the number of times interest is compounded. How can I understand this? From this example, find the final amount of $100 investment after 10 years at a rate of 5% interest compound annually, quarterly, and daily. This is a very simple exercise. We'll need to use this formula. P is the principal, means the initial amount, which is $100, and 1 is a fixed number. R is the rate. The rate here is 5%, means 0.05. Change it to decimal. N is the number of the compound per year. For example, if we take annually means in the same year, just once a year. So we put here 1 and 1 here. This is the N, representing the N. And T is the number of years. Means I want to calculate this after 10 years. So the number or the sum of money will be 162.89 after 10 years. But if we do this calculation quarterly, means 4 times a year, and after 3 months you finish, and then invest the same amount again for another period of 3 months, and then another period of 3 months for 4 times per year. So you need to change this number to be 4, because 4 times a year, and put here 4 also, and keep the rest. So you'll get 164.36. You will increase a little bit from 2 to 4. If you do this daily, means you finish this operation every day and get the sum of money and invest it for the next day. So you need to put 365, means the number of days per year here, because you will do this operation 365 times, and put it here. The practice on this in page 367, same exercise, from number 29 to number 34. Let me take some of them. For example, 29. Find the final amount for each investment. $100 at $1,000 at 6% interest compounded annually for 20 years. I think this is easy. Let me take myself, for example, 34. 1,800. So A equals 1,800 at 6.65%. means 1 plus 6.65%. If you change it to decimal, it will be 0.0565 over. He said compounded daily. Daily means 365. Close the brackets. For 6 years, you need to get this number again here and times 6 years and get this by calculator. Done. And your practice here is this. I'm gonna upload this paper or papers on the Google Classroom. It includes the description and also the practice you need to do, which is this one, by the end of each session. Good luck. Bye bye.